Thank you for having me here today. I really appreciate the opportunity to come and speak to you, my neighbor. I'd like to start out by thanking my co-authors, Tatsu and Percy, who are at the Stanford NLP group, and this is joint work with them. My name is Hugh, and today I'm going to be talking to you about evaluating generative language models. So I'd like to start out with a fundamental question, which is, what are the goals of natural language generation? To ground our discussion, I've taken an excerpt from OpenAI's recent large language model, GPT-2, and put it here. As you can see, this sample is pretty high quality. In particular, all the green words correctly relate to a story about discovery, while all the blue words correctly relate to something about unicorns. But is this all we want from a generative model? And to evaluate it, do we just want to look at the quality of a few samples and see whether they're good or not? Let's imagine I had another model that outputted this as a sample. Atticus said to Jem one day, "I'd rather you shot at tin cans in the backyard, but I know you go after birds. Shoot all the blue jays you want, if you can hit them, but remember it's a sin to kill a mockingbird." This is actually from a famous American story called To Kill a Mockingbird by Harper Lee. And so it's a really good excerpt and a really good story. But a model that outputted this would not be a really good model, because we don't want our models to just copy existing stories. We want them to be able to generate new ones. You might think this is not a big deal. Maybe we can just evaluate the quality of the generated stories and have a plagiarism checker to make sure that we're not exactly copying. But the problem is more subtle than that. Imagine if we had this as an output. To save everyone some time, I've highlighted all the words in blue, which are different from the previous excerpt. This story is not quite as good as the previous one, but it's still pretty good, and in particular it has 0 foreground overlap with the original story, suggesting that it's very tricky to catch this plagiarism example. So clearly this does not work, and even though this is a contrived example, it raises some interesting questions about diversity. How much diversity is enough for a generative model? Is it enough to substitute a few words here or there? What about paraphrasing each sentence just a little bit? There are an infinite number of ways to cheat with under-diversity, and no easy way to quantify this cheating by just looking at the quality of a few samples. This is the first important point of the talk. We believe that generative language models should output both high-quality and diverse responses, and that both of these are important, and that the proper evaluation should make sure that the generative models capture both of these criteria. In particular, the current gold standard of human evaluation does not ensure these two things. We've already seen a little bit of it with the previous example. If you hadn't read To Kill a Mockingbird before, you might assume that this is actually a very good sample and you wouldn't recognize it necessarily as plagiarism. In fact, the problem is even more subtle, and we'll see a little bit more of it by looking at an example task of summarization. Here we want to generate short news headlines from the articles. And as an example, political leaders in Israel united in prayers for Ariel Sharon as the prime minister underwent surgery after suffering a stroke. And the potential output is Sharon has stroke for stroke. Is this machine generated or human generated? It's machine generated because the headline makes no sense. And there's no pun here, even though you might think that there is. It's just a nonsensical output. So this one's pretty clear. Let's take a look at another context. The Buffalo Bills sacked Tom Donahoe as president and general manager on Wednesday, fulfilling expectations of a shakeup. And the output is Bills sacked Donahoe as president and GM. Is this machine or human generated? It actually turns out that this is also machine generated, but it's much harder to catch this issue because it has an under-diversity issue. It becomes clearer, though, when I highlight parts of the context and you see that the output is actually a strict subsequence of the context. If you compare this to the reference headline, which is NFL's Bills shake up front office, it's clear. In fact, this model given here, even though it's able to generate coherent outputs, is unable to generate most of the reference sentences, including this one, suggesting a strong under-diversity issue. In fact, no existing evaluation of natural language generation captures both the elements of quality and diversity that we think are important. Human evaluation, as we previously discussed and just seen, captures quality really well, but can be cheated by under-diversity. Meanwhile, statistical evaluations like perplexity are very good at capturing diversity since they are a valid divergence between distributions, but unfortunately, they do not correlate very well at all with human notions of sample quality. Other evaluations, such as reference-based evaluations like Blue or Rouge, which measure n-gram overlap between the reference and the generated outputs, or learned metrics such as ADAM, which try to mimic human judgments by learning a model to mimic them, are quick and easy to calculate, but unfortunately, they neither capture quality as well as human judgments, nor do they capture diversity as well as rigorous statistical evaluations. So we're kind of stuck. Our proposal to fix this is to unify both human and statistical evaluation into a single statistically principled metric. We do this by building off of the human judgment framework, which is standard. We first take reference sentences from the test set as well as model-generated utterances and mix them together. We then ask a judge to say whether something is machine or human-generated, exactly as we did in the example. And then we measure the quality of the model by measuring the errors of the judge. If the judge makes a lot of errors, it suggests that these distributions are harder to distinguish and thus closer together. Of course, as we mentioned, if we use a human as a judge, we suffer from being unable to capture the under-diversity issues. We get around this by replacing the human classifier with the optimal classifier. In particular, the optimal classifier is able to catch low-quality issues because low-quality samples can be easily distinguished as coming from the model. It's also able to catch under-diversity issues, since if you're under-diverse, it means that you must be placing more mass on certain sentences than the real reference distribution, and the optimal classifier will also be able to recognize that these sentences come from the model. Perhaps best of all, the optimal classification error is an intuitive metric because it directly measures the proportion of samples which are bad, and bad samples are defined as either low quality or low diversity samples. Of course, you might ask the natural question, how do we estimate the optimal classification error? You might think that this looks a lot like the discriminator of a GAN, and that you could just learn a classifier. Unfortunately, this doesn't work because you can never have any guarantees when you learn a classifier of how close it is to the optimal classifier. In particular, if a generative model gets a good score on a learned evaluation, you can never tell whether it's a good generative model or just a generative model that's exploiting the weaknesses of a bad classifier. And so this doesn't work because you never have any guarantees. Our key insight to fix this is that you only need access to two features to optimally classify sentences. Let me explain. For each sentence in the reference set, we collect two values, p model, the probability of the sentence under the model distribution, and pref, the probability of a sentence under the reference distribution. We then map it onto a 2D plane and then classify along the y equals x axis. So this is important, so I want to give it a little bit more extra emphasis. The sentence here actually comes from the reference set and indeed has a higher pref than p model, which means that it's more likely to appear under the reference distribution than the model distribution. This places it above the y equals x line, which means that our classifier will correctly classify it as coming from the reference set. Of course, another question that might come up is that you don't actually observe pref because you only have samples from sentences in the wild. You don't have the actual underlying generative distribution, or else we wouldn't have to worry about generative modeling in the first place. So we need to find something that we can replace pref that is actually measurable but still hits our purposes. Our answer to this is to actually use humans. So in particular, we use crowdsourced estimates of typicality as a substitute for pref. Concretely, what we do is we ask 20 crowd workers to rate a sentence from 1 as rare to 5 as common, and we define the human judgment score as the average of their typicality judgments. These, to note something, these judgments are in context. So this isn't for the evaluations just how likely is this sentence. It's how likely is this sentence given the context. So on Reddit, we find On Reddit, we're able to measure the empirical frequency of the sentence as a proxy for PREF. Because there's a lot of duplicate sentences like thank you, so we can get a good estimate of PREF for a lot of these numbers. And we find that the human judgment score is actually highly correlated with PREF. And thus, we're able to reasonably think that we can substitute in HJ when we need PREF.
So how do you calculate PREF and P-model?
So P-model we can directly get from the model because the models will, like in these for autoregressive models for language.
Usually, classifier trained with the like reference set and the model generated text.
The models we used are autoregressive models, so they give a probability for each sentence that they output, and that is P-model.
Is it like a language model?
Yeah. Or for we do language models. We also do conditional tasks like summarization. But we can get P-model from there. For PREF, we can't get PREF for most tasks. But for Reddit, we can just simply do the empirical count of the sentence divided by the total number of sentences. And when the count is large, you can get an estimate of PREF. It doesn't work if the count is 1. But we use this to validate that human judgment is a reasonable proxy. And going back to our original setup, we now replace PREF with human judgment. Note that the optimal classifier line is no longer along the y equals x axis because human evaluation is merely monotonic with PREF. However, luckily for us, it's still like a monotonic classifier, and we can learn this with high confidence in 2 dimensions given the data points that we have. And so, to recap, what we do is we mix model-generated and human-generated sentences together. We collect P-model and human evaluation for each point, and then we learn a classifier on these points. And then we measure the error of the held out, we measure the held out error rate of this classifier, and we use this as a judgment of how good the model is. We call this one note here is that this gets around the difficulty of learning a classifier that we mentioned earlier because this is actually in 2 dimensions versus the original one is in high dimensions. The key insight here is that we use the human brain, which has a very good intuition about how to generate the sentences, to decompose the problem into a much simpler problem so that this solution is actually tractable. In particular, HUSE actually has some very nice guarantees. The first is that HUSE will always beat human eval. And this is natural to see because HUSE literally takes human evaluation as one of its inputs. In particular, this gap between how good humans do and how good HUSE, which is our estimate, does, is actually interpretable as the gap due to model underdiversity. If humans can catch all the quality defects, then any other defects in the model must be due to underdiversity. In addition, HUSE upper bounds the optimal classification error. And this is easy to see because the optimal classifier is simply the best possible classifier over all possible classifiers, of which HUSE is but 1. This is very nice because this means that HUSE does not give false negatives. If HUSE says a model is bad, the model is definitely bad. Perhaps even nicer is that our estimate is tight if you can perfectly reconstruct PREF from human judgments. Although this is more of a theoretical thing since it's not going to be perfectly reconstructible. So we can see HUSE in action by returning to our previous task of summarization and using it to see how good models are here. In addition, we also use HUSE to understand trade-offs between model quality and diversity by examining a standard decoding procedure called temperature annealing. Temperature annealing exponentiates the last layer of a neural network, which in practice means that it upweights the high confidence outputs at the cost of suppressing the lower confidence outputs, thus trading off diversity for better quality. So, as before, we take each sentence and we map it onto the 2D plane. Here you can see that both headlines do quite well according to human evaluation, so they're both very high on the y-axis. However, the S&P headline is very likely according to the model, so it's on the upper right, while the NFL's Bills headline, as we discussed earlier, is very unlikely under the model, so it's on the upper left. We do this for every single sentence in the reference distribution, as well as all the model-generated sentences. Note here, if you just look at the quality using human eval, these distributions are very hard to separate out because they have very similar quality judgments. However, when you add p-model and diversity into the mix, they become highly separable. And the main reason this is the case is because the model is incapable of generating the majority of the reference headlines, suggesting a strong under-diversity issue. Of course, the model here is actually a temperature and yield model, so we applied techniques to reduce the diversity of the model to increase the quality. So you might ask, well, what if we don't do that and we just sample strictly from the model? This is the plot that results from that. And if you note here, this distribution is actually largely separatable just by human judgment because the model will constantly output very low quality samples. These two examples suggest the existence of a quality diversity trade-off, which HUSE allows us to precisely quantify. Here's how we do it. We can plot a model's HUSE score on this 2D grid, where the upper right is a perfect model, according to our metric. On the y-axis, we define HUSE Q as HUSE using only the human evaluation, which is basically a measure of quality because humans capture quality. On the x-axis, we have the diversity, which is basically all of the error that's caused from HUSE, but not attributed to be from the human quality score. Models on the upper left of this spectrum will generate high quality responses, but perhaps at the cost of being a little bit under-diverse or generic. Models on the lower right will be quite diverse, but unfortunately may generate invalid or ungrammatical responses once in a while. Summarization lands pretty high on the quality spectrum at 0.6 and has almost perfect diversity if you don't do any temperature annealing. If you then add temperature annealing, you get a decent gain from quality. However, this only comes at a substantial cost to diversity. And in particular, if you note, the arrow doesn't get any closer to the top right, suggesting that this makes the model worse off overall, according to HUSE. We also quantify this with chit-chat dialogue, as well as story generation, and find similar stories, which is that techniques to improve quality, such as temperature annealing, come at a great cost of diversity and overall goodness of the model. To recap, we think both sample diversity and quality is important in generative models, and that the ideal evaluation should make sure that generative models have both of these criteria. In order to solve these issues, we see that human evaluation does not capture the diversity component of generative models. And even though it's been used as a gold standard, we propose HUSE instead, in which we unify human evaluation with statistical evaluation into one principled metric, which can capture both diversity and quality. Our metric is ready to use on GitHub. You can find tutorials for how to use HUSE, as well as documentation and the code to replicate every experiment that you have seen in this presentation, as well as in our paper. To use HUSE, all you need to do is to provide the model probabilities, as well as your human annotation scores. Our code will take care of the rest. That's all, and thanks for listening.
The diversity you use in this project sounds a little bit different from the generic meaning of the diversity. Usually, previous works on summarization or any diverse sequence generation works measure diversity by number of distinct generated outputs, or like the measured by model or human judgments.
Yes. So we used a different definition of diversity here, and the reason why we thought diversity is a kind of term that's there's no ironclad definition, and for here, it's sort of we think that there's two large components of how close you fit to a distribution. One of them is whether you generate whether you generate good responses, which is the quality, and the other is sort of whether you cover the distribution, which is diversity. We measure this coverage by using p-model to check whether you place coverage over all of the reference examples. And so it's not exactly the same as the number of distinct examples or even the entropy of the generated model, but it's sort of another way of thinking about diversity.
Doesn't the theoretical guarantee of HUSE outperforming the human judgments makes its performance weaker? I mean, does it guarantee that this is good good measure because it's still based on human judgments. So
this guarantee is that if you have enough samples, that you can't, at least no matter how bad HUSE is, if you have enough samples, you won't do any worse than the current gold standard, which is humans. So we're not dropping. And in particular, like the closer that human judgment is correlated with PREF, the closer we get to the optimal. So of course, if for your task, human judgment is totally uncorrelated with PREF, we just are the same as human judgment. But if we're perfectly correlated, then we're the same as the optimal classification error. And if you're somewhat correlated, we're somewhat in between. And so we don't give any guarantees because it's very hard to check how closely correlated you are with PREF in practice. But it's just, we've shown on the Reddit distribution, it's very correlated. And we assume that it transfers over to other data sets. All right. Thank you for listening to the talk. I really appreciated coming and talking to you today, Neighbor.